Welcome to Shanti-Peace for Mathematics. In the previous video, we have learned a proof of Lagrange mean value theorem, which states that let f be a function from ab to r be satisfies the first condition, that is f is continuous on closed interval ab. Second condition, f is differentiable. There exists at least one c in open interval ab such that f dash of c is equal to f of b minus f of a upon b minus a. Those who have not gone through that video, a link is given in the I button. You can go through that and visit and watch that. There is also one more things we have discussed, that is called another form of Lagrange mean value theorem. Instead, in that we have, instead of this closed interval, we have taken the closed interval a to a plus h. So you have here f is continuous instead of a to a plus h. Here it is open interval a to a plus h, and the output is there exists at least one theta in between 0 and 1 such that f of a plus h is equal to f of a plus h into f dash of a plus theta h. So this is another form of a Lagrange mean value theorem. We'll discuss some of the example of these two statements in this video. So let us start with the first example. The first example says that verify LMVT for the function f of x is equal to lx square plus mx plus n in the interval ab. So the question is to verify the LMVT, that means whether we can apply the Lagrange mean value theorem onto this function, and also we have to check whatever the value we get for the c, it has to be lies in this interval. So here what we have, the function is this, f of x is equal to lx square plus mx plus n, where x belongs to closed interval ab is given. This function f is continuous due to this is a polynomial, as well as it is differentiable as the same reason. Continuous on closed interval ab and differentiable on open interval ab, as f is a polynomial function. So we can able to apply LMVT. So hence both the condition of LMVT are satisfied. Therefore there exists at least one c in interval ab such that f dash of c is equal to f of b minus f of a upon b minus a. What is the function f we have given? The function f is lx square plus mx plus n. So what is the derivative of that? It is 2lx plus m. That is the derivative. So f dash of c will gives me 2lc plus m, where c is some constant, is equal to f of b, that is lb square plus mb plus n minus l a square minus m a minus n upon b minus a. You just observe this n will get cancelled out, and from these two terms m is common out, and from these two terms l is common. So we're left with l b square minus a square plus m b minus a upon b minus a. You just observe that in the numerator it will be b square minus a square, so that will be factorized as b minus a, b plus a, and b minus a is also here, so where that quantity is also common. So therefore we'll have 2lc plus m is equal to b minus a is common out. You just observe that, and what is left here is l into b plus a plus m. So it is L into B plus A plus M upon B minus A. And this B minus A is get cancelled. So we'll have L into C plus M is equal to L into B plus A plus M. M will get cancelled. So we'll have 2LC is equal to LB plus A. And therefore the value of C which we obtain due to this L is cancelled out, we'll have B plus A upon 2. And this is the midpoint of A and B point. So that is always belongs to the open interval AB. So hence what we can say is the theorem is verified. Why it is verified? Because we can apply this LMVT onto this function, and the value of C which we got, it is lies inside this interval. So hence this LMVT is verified. Let us solve one more example. The question is the same. Verify LMVT for the function f of x is equal to ln of x in the interval 1 to e, and hence find the value of c. The c is that the value is we got using the LMVT. So first one should note that here the function f is a logarithm function and is continuous and differentiable over this interval. So I should write that here the given function f of x is equal to ln of x is continuous on closed interval 1 to e and differentiable on open interval 1 to e. Hence both the condition of LMVT are satisfies. Further, there exists at least one c in the interval 1 to e such that f dash of c is equal to f of b minus f of a upon b minus a. But what is the function f of x here? It is ln of x. So it is f dash of x will gives me 1 upon x. So f dash of c therefore will have it is 1 upon c. What is f of b? Here a is 1 and b is e. So it is f of e. ln of e will gives me 1 and ln of 1 will gives me 0 upon e minus 1. So that's why this is 1 minus 0 upon e minus 1 will be, which will gives you 1 upon e minus 1. So hence the value of c we have it is e minus 1. And one should note that this e minus 1 which is belongs to the interval 1 to e. So hence the theorem or LMVT is verified. That we can say from this. Let's gives you one problem to do it as yourself. So the question is verify LMVT for the function f of x is equal to x minus 1, x minus 2 into x minus 3 and find value of c. This is a question you can try by yourself and solve this. Let's have another example. Find the value of theta in LMVT for the following function. The f of x is equal to e power x, where x is belongs to closed interval 0, 1. Now here instead of c they have used the word value of theta. So that means we have to use the another form of LMVT. So as you know that the another form of LMVT says that f is continuous over the interval a to a plus h, f is differentiable over a to a plus h, then there exists a theta, it is in between 0 and 1 such that f of a plus h is equal to f of a plus h into f dash of a plus theta h. This is the theorem we have discussed earlier in this video and also in the previous video if you have watched that. Now the question is, we have to calculate this theta here from this. So first one should note this f is continuous over this interval and f is differentiable also over on this interval. So that we should write that f is continuous because it is exponential function, and we know that the exponential functions is continuous and f is differentiable on open interval 0, 1. Then by LMVT I should write by another form of or alternate a form of LMVT. We have f of a plus h is equal to f of a plus h into f dash of a plus theta h. This is a, where this theta for some theta is belongs to 0, 1, in between 0 and 1. Now what is a to a plus h here? The interval is given is 0 to 1. So therefore the value of a is 0 and the value of h will be 1, because a equal to 0 we have a plus h is 1. So the value of h is 1 and value of a is 0. That we should note here. So if I can call this as equation 1, then according to this equation 1, therefore from 1 we get, as per this it is a plus h. So it is a plus h is 1. So it is f of 1 is equal to f of 0 plus h into f dash of, it is a plus theta h. The value of a is 0. So it is 0 plus theta h. H is 1. So it is 0 plus theta into 1 for some theta between 0 and 1. Now what is the function f of x is given us? It is e power x. That is the function we have. So e power 1, that means f of 1 is e power 1 will gives you e. E power 0, that is f of 0, that will gives me 1 plus h. H is also 1, so I am not writing it, 1 into, so it is f dash of theta we have. So it is e minus 1 is equal to f dash of theta. But what is f of x is e power x, and we know that the f dash of x is also e power x. So therefore it will gives me e power theta is equal to e minus 1 due to the derivative of f dash is e power theta. And if I want to calculate what will be the value of theta, then theta will be ln of e minus 1. And this ln of e minus 1 is need to calculate. That is the value of theta which is in between 0 and 1. And this completes this example. Now we'll discuss the next example in which many a times this Lagrange mean value theorem is used to establish some inequalities. So for example, I'm taking certain examples here and will use LMVT to prove that inequalities. The first one that I'm taking using LMVT, so that 0 is less than 1 by x cos inverse of sin x upon x less than 1, where your x is belongs to 0 to pi by 2. So here the question is to using LMVT we have to establish this inequality. And you just see this inequality, what is this inequality says. Let us do some rough work here. If I multiply x both sides, then this will gives me 0 less than cos inverse of sin x upon x less than x. If I apply cos, then it will be cos 0 is less than sin x upon x less than cos x. We know that cos 0 will be 1. So it is 1 is less than sin x upon x is less than cos x. And you should just note that this is of the kind, or we can write down this is as 1 less than sin x minus sin 0, because sin 0 is 0 upon x minus 0 is less than cos x. So it's kind of LMVT we have to apply for the function sin x in the interval 0 to x, and we have to establish such result. That is the objective, and that is the way is to looking this type of inequalities. So what you have to start with to prove this one, or to establish this inequality, you have to start by defining some function. On that function you have to apply LMVT. So that function is, from this I can say it is a sine function, because it is sin x minus sin 0 is there. So it is in the interval is 0 to x, where x is between 0 to pi by 2. So I'll start with the defining a function, that is any x is in the interval 0 to pi by 2. Define the function f, which is from 0 to x to r, as f of x is equal to sin x for every x is in between 0 to x. Now this function here, f is continuous on closed interval 0 to x, and f is differentiable on open interval 0 to x. Therefore by LMVT, what we can say, there exists one c is in between 0 to x. Okay, so we'll say there exists at least one c, it is in between 0 to x, such that f dash of c is equal to f of b minus f of a, but b is x here, so it is f of x minus f of 0 upon x minus 0. What is fx here? Fx is sin x. So the derivative of sin x, we know it is a cos x. So it is cos c equal to sin x minus sin 0 upon x minus 0. So that will give me sin x upon x is equal to cos c. Now the question is to obtain this inequality. And here we have given this, that is a c is in between 0 to x. So we'll start with that. Given that 0 less than c less than x, not given, but here we have this. Now I have to make this cos c here, so I can use this quantity. So I apply the cos both sides. Cos 0 is less than 0 to cos c is less than cos x. See, this x is for any x which is between 0 to pi by 2, cos function is positive, so there is no problem with the sign change. The cos 0 will gives me 1, that is less than the cos c. The value of cos c we can write from the equation 1 is sin x upon x is less than cos x. Now if I apply cos inverse both sides, so that's it is cos inverse of 1 is less than cos inverse of sin x upon x is less than x. Now cos inverse of 1 will gives me 0. So that's why it is 0 less than cos inverse of sin x upon x is less than 1 if I divide 1 by x here. So hence we got this inequality. That is our objective, is to we achieve from this. Let us solve one more example of such type. So the question is, using LMVT for x which is greater than 0, prove that log base 10 x plus 1 equal to x into log base 10e upon 1 plus theta x, where your theta is between 0 to 1, and hence deduct that x into log 10 base e is greater than log 10 base x plus 1 is greater than x into log 10 base e upon 1 plus x. So don't be confused by looking at this expression. The hint is given using LMVT. We have to achieve this, and since it is given one theta, it is in between this. That means we need to use the alternative statement of LMVT. But what will be my function? I have to start with. As you can see that on this side it is given that log of x plus 1 base 10, and here it is 1 upon, so the derivative of log function we know it is 1 upon x. So it suggests me that we have to define a function, a log x, but the interval is now, instead of x, it is x plus 0 to or 1 to x plus 1. So I'll define here f from 1 to 1 plus x to r as f of x is equal to log base 10x. Now this function f is continuous and it is differentiable over open interval, that we should write. Here f is continuous on closed interval 1 to 1 plus x, and f is differentiable on open interval 1 to 1 plus x, then by LMVT. Now here I have to use the alternating form of LMVT. We have, there exists at least one theta which is between 0 and 1, such that f of a plus h is equal to f of a plus h into f dash of a plus theta h. Now what is the value of a, what is h? Since here the interval is 1 to 1 plus x, so obviously the value of a is 1 and a plus h is 1 plus x, so that will implies the value of h is x. So a is 1 and h is x. We'll put that one here, then this will implies, that is the function f, we have log of 10 base 1 plus x, so it will gives me log of a plus h, log 10 base a plus h is equal to log 10 base a, the function is log x that we have defined. So it is log 10 base a plus h into f dash. Now f of x is log 10 base x, so it is log e base x upon log 10 base e. So the derivative of this one is f dash of x is 1 upon x, and this quantity, if I want to write in the numerator, that I can write down log of e base 10. So it is log e base 10 upon x. That is the derivative of f dash. Now a, we have to substitute this value. So that will gives me h is already there, log e base 10 upon x is there, but instead of x we have it is a plus theta h. So it is a plus theta h. Now as I told you, the value of a is 1 and the value of h is x. So put a is 1 and h is equal to x. We get log of 10 1 plus x is equal to log of 1 base 10 plus h, it is x, log 10 base e upon a is 1 plus theta, that is there, and x, h is x, where your theta it is belongs to open interval 0. So that is the quantity which we have to prove into the statement log 1 plus x is this, because this value will be 0, log 1 is 0. So that's why it is, we got log 1 plus x base 10 will be x into log e base 10 upon 1 plus theta x. Now the second question was to calculate or need to establish this relation, this inequality. Here it is this function. So I'll start with, doing that one, I'll start with a theta is in between 0 and 1, and we'll make this things 1 plus theta x, 1 upon 1 plus theta x, that is equal to this. So we'll make out with this expression here. As I have in the middle, we have this expression, and that is the things exactly we have here. So we'll make this quantity into the middle. So for that I have to multiply x both sides, will gives me this. If I add 1, then it will gives me this, and if I take the reciprocal, then the inequality will be changed, 1 upon 1 plus x. Now what will be this? You just observe that this quantity is missing, so I'll multiply this quantity from into the both the side. So it is, that will implies x into log e base 10 is multiplied x log e base 10 upon 1 plus theta x greater than x log e base 10 upon 1 plus x, and just put this value now back, that is from the previous expression we got, it is log 1 plus x base e greater than x log e base 10 upon 1 plus x. So exactly this expression we have to prove into the given problem, and we have achieved that. Let us solve a couple of more examples. The question is, using LMVT, prove this 3 plus 1 upon 28 is less than cube root of 28 is less than 3 plus 1 upon 27. Now this will suggest something. Here nothing is given, no function is given. You have to construct of your own function and to discuss this one. And this will suggest that the middle quantity is your function. So let us define a function f from x to x plus h to r as f of x is equal to cube root of x for every x is in this interval x to x plus h. Because this is cube root of 28 is given to us, and that will suggest that this has to be a function. Now we have to apply the LMVT onto this function. So here the function f is continuous on this interval x to x plus h for any x positive, this is true, and f is differentiable on open interval x to x plus h. We have this. Now by LMVT, what we can say, we have there exists at least one theta in between 0 and 1 such that f of a plus h, that is x plus h, instead of a we have x written here, f of x plus h into f dash of x plus theta h we got. Now your function f of x here, it is x raised to 1 by 3. So this we got x plus, and I am taking h is equal to 1 here. And why I am taking, and what should be the value of x? Because you just see this one, what you have here, it is 28. So if I want that this quantity here, then this should be 28. X plus h should be 28. So that's why I am taking this x is equal to 27 and h is equal to 1. So this will become 28. So it will gives me 28 raised to 1 by 3, because our function is f of x raised to 1 by 3. And that is my objective, to obtain the extreme and value of this square root of 28. So that I am taking. And so this will gives me, this is f of x plus h is equal to f of x. X is, I have taken 28. So it is 27 raised to 1 by 3, this one, if I put the value of x here. That is 27 raised to 1 by 3, which will be gives me 3. H is 1, so I am not writing that 1 here. And that f dash, so we have a derivative of this f function, that is 1 by 3 x raised to minus 2 by 3. So that's why this will gives me 1 by 3 1 upon x raised to 2 by 3, that is x plus theta. X is 28, so 27, so x is 27 plus theta, h is 1 raised to 2 by 3, and this value is 28 raised to 1 by 3. So finally what we got is 28 raised to 1 by 3 is equal to 3 plus 1 upon 3 into 27 plus 8, sorry, theta raised to 2 by 3. For some theta, it is between 0 and 1. Now this value is satisfied, or I can say a theta which is in between 0 and 1. Now I have to make out this quantity, because I need to have 28. So I have to make out this 27 plus theta. So I'll add 27 both sides. So 27 is less than, sorry, 0 plus 27 is this. 27 plus theta is less than 28. Raised to 2 by 3. So it is 3 less than 27 plus theta raised to 2 by 3. So 27 2 by 3, that is a square is also there. Less than 28 raised to 2 by 3. If I multiply 3, so that will gives me 27 again, because 3 square, that will be 9, and multiply by 3, that will gives me 27. 3 into 27 plus theta raised to 2 by 3 less than 3 into 28 raised to 2 by 3. And 1 upon this will gives me, this inequality will be changed. So that's why this will gives me 1 upon 328 raised to 2 by 3 less than 1 upon 3 into 27 plus theta raised to 2 by 3 less than 1 upon 27. And if you can add 3 here, therefore this will give 3 plus 1 upon 3 plus 28 raised to 2 by 3 less than 3 plus 1 upon 3 into 27 plus theta raised to 2 by 3 plus, sorry, less than 3 plus 1 upon 27. But this value we have obtained it, that is 28 raised to 1 by 3, and hence we got our inequality which we have to prove, that is this is 28 raised to 1 by 3 is less than 3 plus 1 upon 27. Okay, now what we can see is we have to just look at our expression. In expression, it is the only things is left is this 3 plus 1 upon 28. Here we have achieved on this side. So this quantity, for that one we have to looking at over this, especially for this one only. So you just observe that 1 upon 3 into 28 raised to 2 by 3 I may write as 27 raised to 1 by 3 into 28 raised to 2 by 3, which I can say it is greater than 1 upon 28 raised to 1 by 3 into 28 raised to 2 by 3, because 27 is smaller than 28. So if I take the reciprocal and cube root, we'll have this, and this will be nothing but the 1 upon 28 raised to 3 by 3, which will gives me 1 upon 28. So this value is actually greater than 1 upon 28. So hence what we get, it is in the from the previous quantity 3 plus this. So I should write 3 plus 1 upon 28 is less than 3 plus 1 upon 27, or 3 into 28 raised to 2 by 3 less than cube root of 28 is less than 3 plus 1 upon 27. This is the exactly the expression which we have to prove into the given statement. Let us solve one more and the last example for this video. Question is, use LMVT to prove b minus a upon 1 plus b square is less than tan inverse of b minus tan inverse of a less than b minus a upon 1 plus a square. If the value of a is less than b, and hence deduct that pi by 4 plus 3 by 25 is less than tan inverse of 4 by 3 less than pi by 4 plus 1 by 6. Now first of all you should note that what is the expression is given to us and how we can proceed for this example. The expression is given in this format, and if you just do some rough work by dividing b minus a, as b minus a is a positive quantity due to this expression, if I divide b minus a from this side, we'll have b minus a is here. So this will suggest that what should be your function f to apply the LMVT on that function. So it will suggest that the LMVT is the tan inverse of x, which is in the interval a to b, and then we can apply the LMVT on. So we'll start with this idea and proceed to doing this, defining the function f from a to b to r as f of x is equal to tan inverse of x. That is our objective. Now, so that's the value, that is for every x is in between a to b, we have defining this. Now here f is continuous on closed interval ab, and f is differentiable on open interval ab. Then by LMVT there exists at least one c is in between ab, such that f dash of c is equal to f of b minus f of a upon b minus a. The f dash of c we have, it is f of x is tan inverse of x So f dash of x, we have 1 upon 1 plus x square, that we know. So f dash of c will gives me 1 upon 1 plus c square. So therefore this will gives me 1 upon 1 plus c square is equal to f of b, that is tan inverse of b minus tan inverse of a upon b minus a. This is the expression we have. Our objective is to establish this inequality. So as we have did it in the previous all the example, we have to start with this. Your c is in between a and b. Now you have to make out this expression, that is 1 upon 1 plus c square. So take the square both sides. So this will gives me this, and if we add 1, hence this will gives me this. And if you do the reciprocal, it will gives me 1 upon 1 plus b square is less than 1 upon 1 plus c square is less than 1 upon 1 plus a square. Due to the inequality will be changed if you do the reciprocal. Now you just substitute this value 1 upon 1 plus c square here. So therefore that will gives me 1 upon 1 plus b square is less than tan inverse of b minus tan inverse of a upon b minus a is less than 1 upon 1 plus a square. If you multiply by b minus a both sides, we have achieved our expression that we want to prove. Now the question is, second question is to establish this expression. In that you have to substitute some particular values of a and b. So you will have this. Now you just observe from this one, suppose you have b minus a again here, and this b minus a is also again here. Now you just observe that instead of b you will have 4 by 3, and instead of 1 it is, sorry, instead of a you will have 1. So tan inverse of 1 we know it is, tan inverse of 1 is pi by 4, and that pi by 4 is here. So instead of making this, you just need to prove that 3 by 25 is less than tan inverse of 4 by 3 minus pi by 4 is less than 1 by 6. So you have to put some appropriate value of a and b, so you will have this. Now what should be my a is pi by 6, oh sorry, a will be 1 and b will be 4 by 3, that it will suggest. So what we can put here, put a is 1 and b will be 4 by 3. That will gives me this, it is 4 by 3 minus 1 upon 1 plus 16 by 9 less than tan inverse of 4 by 3 minus tan inverse of 1, which is pi by 4, less than 4 by 3 minus 1 upon 1 plus 1. This will gives me 9 plus 16, so it is 25. And so it is, and this will gives me 3, so it will gives me 3 by 25. This expression is 3 by 25, and this expression is 1 by 3 in numerator, and in denominator it is 2, so it is 1 by 6. So that's why this will gives me 3 by 25 is less than tan inverse of 4 by 3 plus, sorry, minus pi by 4 is less than 1 by 6, and adding pi by 4 from both sides, we have achieved our inequality which we need to prove. So in that manner you have lots of other examples I may given you as an assignment. You proceed for that, you try to solve that one. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.